between this topic and also finite. The finite subgroup modular forms and hypergeometric functions.
Okay.
They are closely related. It's actually, yeah.
And Calabi variety or finite field too?
Yes.
It's
yes,
actually
yeah.
I start from K3 surfaces. So I start from
I have seen your paper with the Vadim on the SP4 cases, the Calabi-Yau 3 poles.
And we are glad that eventually we're able to use, to me, what I mentioned later, the Atkin and Swinton diet congruences, in some form, triple congruences. And the way we solve it is more or less borrowing some idea in a very special form of the formal group. It's somehow it's an idea go back to the walk, how he handled his But I'm not going to mention that this talk. It's purely focused on these two players, the groups and the modular forms. Yeah.
You're going to talk about a little bit about non-congruence modular form as well, right? I'm assuming. Right?
Non-congruence modular forms will be one of the main players for this talk, because I was told that maybe the audience is wanting to know some results I've done with A.O.L, Atkin, and Winnie Li.
Okay.
So this is more on modular form side for this talk.
Jitendra, can we begin?
I think we have still 3 minutes to go. So
let me see whether my pen is working. Yeah, it's working.
it's right now 2:27, so we should start. Let's wait for 2 more minutes to see if few more people join us. Okay. Then we can go ahead.
So Professor Winnie Li talked to you before the talk for her talks?
She did. We have a couple email correspondence.
Yeah.
Yeah, she usually works really late into the evening. So this time of the day, it's for most days, it will be difficult for her, but
yeah, so we will arrange her talk an hour later, maybe 8 p.m. or 9 p.m.
That's helpful that she mentioned it.
Yeah, she mentioned to me.
She also mentioned she agreed already to give her talks.
Okay, if you want, we could.
Yeah. I'm ready.
Could, yes. So, welcome everyone. So this is the last lecture of the first trimester of this year-long program, and we are happy to have Professor Ling Long from Louisiana State University, and she is going to tell us about finite index subgroups of the modular groups and their associated modular forms. Over to you, Professor Long.
I would like to thank the organizers and I mean, scientific committee, boards, and everyone being here. And so my topic is already on the screen. I will talk about two main players. First will be on the group side. It's more on some of the ideas about the implementation. And then there will be some results on the non-congruence modular form, because majority of finite index subgroups will be non-congruence subgroups. Okay. And if you have any questions, do not hesitate to ask me, because I did not prepare too many slides, just to make sure that I'm not going to overwhelm you for the last talk. Right? So let's first start with the group of SL2Z. Then everybody knows it's generated by two elements. One element typically is called S. Now I call it E. It's the element which is a 0, 1, minus 1, 0. In SL2Z, it's order 4. And once you quotient out by the scalar, it's going to be order 2. And the other elements, I use V, which is 1, 1, minus 1, 0. So this is the order 6 element. And the fundamental domain, one of the fundamental domain, instead of the standard one, I'm using this one, which is from Professor Kukwani's paper. It's written in a special polygon. So the fundamental domain is going to be this triangular area. And there are two elliptic points. One is the I here, and then there is another elliptic point, which is rho over here. And these two elliptic points will be useful for another concept, which is called the Bipartite Cuboid, also in his paper. And using this special triangular area, we can do a tessellation of the upper half plane. For example, start from this piece. I can rotate to get to this piece. I can rotate to get to this piece. And then I can do the rotation. There's another rotation around all the two elliptic points. I can get to this piece, etc. So we can propagate the triangular area to kind of get to any other point on the upper half plane. And then the way when we propagate, we will actually get to the cusp. The cusp are relating to the tip over here for this case, which is 0. And there is another one, which is at infinity. So when we propagate, we are getting to the corresponding cusp. And then those are the useful kind of information for putting together the so-called fairy symbols that I'm going to talk about later. That I'm going to just mention, right, not to define it. And there are an important class of finite index subgroups, which will be one of the main topics for my talk. The congruence ones actually is defined by first the idea of principal congruence subgroups. So those are the elements you first fix a natural number. Let me see. Let me get to here. There is a natural number playing the role of a level, and you look at every matrices in SR2Z, which is the modular group, and you look at the kernel of the modulo M kind of homomorphism, and you get to the principal one. And if you have any finite index subgroup which contains one of those principal one, and such a group gamma is said to be congruence. Otherwise, it's said to be non-congruence. It's also a well-known fact that non-congruent subgroups outnumber congruent ones. So there are different measures. I just want to mention this comparison over here. For example, Newman showed that in 1965, there are infinite many non-congruent subgroups of genus 0. And Denning showed that 10 years later, for any given genus, there are only finite many congruent subgroups, including genus 0. So you see that on comparison, when you only focus on genus 0 case, for the congruent side, there are finite many. For the non-congruent side, there are infinite many non-congruent subgroups. This is one measure to see the claim over here. Now, for a given finite index subgroup, I'm going to abbreviate by finite index subgroups. And to describe it, for this talk, I only need to talk about elements in PSR2C because the modular form I mentioned later, most of them will be even weight. Of course, for the odd way, we can add a multiplier. So one result is due to Millington. She actually showed that up to isomorphism, if you fix an index, if you fix the fixed index, you look at the class of all the finite index subgroups within the given index, up to isomorphism, they are in one-to-one correspondence with a pair of permutations in the permutation group Sn. And in particular, E is the image of the matrix. I call it E before. Projectively, the order is 2. And the other kind of permutation is the image of the matrix V. So projectively, it's order 3. And another condition is the group generating by this pair of permutations should add transitively on the numbers 1, 2, all the way to n. And then in this very important paper, the important concept brought out by Professor Kulkarni is finite index subgroups can be described by generalized very symbols or very symbols. So they are actually describing the vertices of the fundamental domains written in a very special form called the special polygon, special hyperbolic polygons. And also the comparing to, if you only have a list of the vertices, they're called fairy symbol. There are also pairing information to make it into, make the fairy sequence into fairy symbols. And he also proved that the conjugacy classes of finite index subgroups are in one-to-one correspondence with isomorphism classes of bipartite cuboids. I'm going to illustrate in the next 2 slides. So let me kind of introduce the idea by using this special example over here, which is the group gamma 04. So consists of matrices, which will be upper triangular. Modulo 4, it will be 0 over here. And this group as a group in TSR2C is going to be index 6. And the way one fairy symbol it's attained can be computed in the following. We start from the standard fundamental domain. We propagate as long as the pairing information has not been, the boundaries has not been fully kind of paired up. So we can rotate to this side. Once we rotate to this side, we'll see that the right boundary and the left boundary can be paired up because from here to here, there is a matrix, it's 1, 1, 0, 1, which is inside this group. And then we continue to propagate in this way and then go down and then propagate in the way you actually eventually you get to all the boundaries. This too will be paired up as well. Okay. And we get to this special polygon. For the special polygon, we take a look at the boundaries by looking at tracing the vertices. So we start from the convention is negative infinity. We go down to 0, and then we go to 1/2. We go here to 1, and then go up to infinity. And for the pairing, so from here to here, you get 1, 1, 0, 1, as what I said. I make a mistake over here. And then the pairing between these two semicircles, you can check that can be done by using this matrix. So you get a list of generators, and the corresponding fairy symbol is this form over here. If you look at the vertices, you look at the consecutive ones, they are forming so-called fairy sequence by looking at the cross ratio. Say, if I look at the cross ratio 0, 2, and 1, 1, the cross ratio is 1 up to actual value, and the same thing happened to here. And the convention over here is this is -1, 0, this is 1, 0. So we get a fairy sequence with the pairing information. The pairing information is obtained by the corresponding arc connecting, or the grand circle connecting the corresponding two vertices. And the 2 and 2 indicates that we're going to do a pairing which is clockwise kind of pairing. So giving rise to this matrix down here. And let me also mention about this picture on the right-hand side, which is called bipartite cuboid. And to get to the bipartite cuboid, what we can do is we first mark the corresponding elliptic points, which are the images of I and rho. In this process, so they're marked into the small open circle, like this one, this one, this one, this one, this one, or the black kind of dot over here. And then we actually connect them if they are, so connecting them means if I draw a line between the first two elliptic points, we are going to look at the images of this line. So if you look at the images of this line, you get to this connection, this one, etc. And then we forget about the blue boundary and the red kind of inner lines. The leftover one, the leftover Y, the connecting the Y circle and black dots are the black vertices that are newly joined, plus the pairing information. So I already pair up. So these two elliptic points, 2 and 2, are paired up. And then down here, there are pair up already. So we get to so-called bipartite cuboid. It's bipartite because there are two different kinds of elliptic points, one of all the two. And the other kind will be all the three. And once we put the label on the corresponding black vertices, indicates which fundamental domain of the SL to Z, how it's propagated, we get the labeling 1, 2, 3, 4, 5, and 6, etc. Then we can read off the two permutation respectively. So to get to E, which is the order 2 permutation, we just read off the pairing correspond to the Y small circle. For example, here you get 1, 2. The next one, the pairing, the adjacent one will be 3, 4. The last one will be 5, 6. And to get to the order 3 permutation, we look at the black dots. And another thing to keep in mind is you have to fix an orientation. Typically, it's going to be clockwise. So you read it as 1, 2, 3, and then down here is 4, 6, 5. All right, so we get to 1, 2, 3, and 4, 6, 5. Okay. So from the group, then you get to the other two types of way describing it. One is the bipartite cuboid, and the other one will be a pair of permutations, E and V. All right. Typically, the way writing it is not unique. There is always up to isomorphisms. All right, but these so are the very
do it by the program.
Sorry?
You do it by the program, right?
Yes. So the program, you mean?
Sage.
Sage. Yeah, I'm going to mention that over here. So everything I mentioned over here has been programmed. Right? Okay. And so you can actually do a lot of different things with computer programming these days. So either you have the presentation in terms of pair permutations, or you use the generalized fairy symbols. You can actually use them to compute different kind of things, including the minimum set of generators, and the index, basic invariance, index, genus, elliptic points. And for the congruence case, you can go back to compute the modular symbol. Or you can actually give you a kind of pair of permutations acting transitively. There are different algorithms telling you whether the corresponding finite index subgroup is congruent or not. And you can also compute intersections of two groups or the unions of two groups.
So these modular symbols are also computed by this Faraday symbol?
Modular symbols, they have more or less they're using, for the congruence case, all right, what I'm trying to say, the modular symbol is mentioned over here. It's once you know your group is going to be congruent, there is a way you can go back to the classical way, which is using modular symbol to representing those groups.
Okay.
And you can also compute a group of normalizers. For given a gamma, you can compute the group of normalizers in SL2R. And for some of the implementation that my former PhD student, Chris Kurz, implemented first in, at that time it's called Sage. Now it's called Sage Math package. So what we call is called the K-Fairy. And later, Professor Molian actually took the implementation and expanded further. My recent joint PhD student, Bao Fan, with Professor Fountain too, further implemented more functions for finite index subgroups, especially including some kind of functions on the bipartite cuboids and also for other triangle groups. So it's make it more general. So this is what I want to talk about on the finite index subgroup side. And I'm going to switch gear to modular forms for the remaining of my talk. So once we have a finite index subgroup gamma of SL2C, if you add on the upper half plane, my notation will be this edge over here, my linear fractional transformation. So if we look at the quotient, the orbit space, and performing a compactification, the compactification corresponding to the vertices I mentioned in the previous picture. So they will be called cusp. So we only need to add finite many cusps to compactify the quotient space. We get to an object which is called a modular curve. And the theorem of Bellier says that if I have any smooth projective irreducible complex curve defined over a number field, then it can be realized as a modular curve for some finite index subgroups gamma of SL2C. And in 2000, the paper published in 2018, another PhD student of Winnie, which is a Wen-Ching attained a modular interpretation for non-congruence modular curve by considering Galois, finite Galois covers with Galois group G of elliptic curves E that only ramify at one point, which is the identity. And when the group G is abelian, then it recovers a classical level structure. When G is sufficiently non-abelian, then it actually gives the modular interpretation for non-congruence modular forms, which is a very nice and fundamental result. And now I'm going to kind of recall the definition for modular forms. If I have a holomorphic or meromorphic function defined on the upper half plane, it is called a vacant modular form. So if you apply the linear fractional transformation for this matrix ABCD inside gamma on Z on the upper half plane, you get to there is an automorphic factor raised to there are integer k for my talk, and k is also non-negative integer and back to f of z for each matrices A, B, C, D. And if you also insert closed conditions at the cusp, then you get to, depending on the application, you get to holomorphic or neuromorphic modular forms. And for later, for my talk, there are two kinds of modular forms which are of importance. First one will be the holomorphic one that also vanish at all the cusps. So they are called cusp forms. If you put together a fixed weight, if it's going to be positive integer, for a fixed weight, if you put together such holomorphic cusp forms, and you get a finite dimensional vector space. And the other kind of modular forms of importance will be when the weight is 0. In this case, f has to be, if you want to get interesting one, f has to be neuromorphic. So what the object is called is a modular function. And for example, the modular J invariant, the modular J function plays a fundamental role and as the kind of the generating function for all the neuromorphic functions for SR2C. And the modular lambda function also playing a similar role for the level 2, the principal level 2 congruence subgroup. And before I get to non-congruence modular forms, I would like to kind of mention about some of the properties for congruence modular forms. So if we look at this one of the most well-known modular form, which is the delta function, is defined as Q is going to be e to the 2 pi I z. Z is in the upper half plane. It's Q. It's infinite product Q times products 1 minus Q to the n to the 24, where the exponent goes from 1 to infinity. If I expand it out just formally and we look at the coefficients, they're called the Ramanujan tau function. And this infinite series start from Q, so if it's 1 normalized, the next coefficient is minus 24 and 252, etc. It's really amazing that Ramanujan, by purely looking at the coefficients, he was able to compute before computers. He discovered amazing 3-term recursion for each prime p. There are 3-term recursions. So if I look at the coefficients, and for the fixed p, he noticed that if you look at the coefficients when you start from the first one, the next one, the recursion occurs to this one, the p power dropped by 1. And then the next one, the p power further dropped by 1. If you look at these 3 consecutive terms, they are relating by 2 coefficients. One will be tau of p, which is independent of which additional integer you're going to insert. And for the second coefficient, it's a power of p, which is p to the 11. And for the delta function, then we all know it's in S, it's a cusp form of weight 12 in SR2C. So this power is relating to the weight. It's a weight minus 1. So this is the first very important observation that he made. The second one, which is equally amazing, is he actually gave a bound for the size of Ramanujan tau function. For instance, at point t, he noticed that the value is going to be between, it's bounded by 2 times p to the 11 over 2. So Ramanujan's 2 discoveries actually kind of motivated a lot of developments for the development of modular forms. For instance, corresponding to these 2 properties, the first property was proved by Model. Okay, so the first property was proved by Model. using essentially, it's in 1917s, using essentially the idea of Hacker operators, which was not there. So it's 10 years before Hacker developed Hacker theory. So it's the three-term recursion I mentioned at 1 are relating to, due to the action of Hacker, the Hacker algebra. Hacker operator put together, there is a Hacker algebra acting on the space of weight K cast forms for congruence group gamma. And the action of the Hacker operators or algebras give a decomposition. So I mentioned that this is a finite dimensional vector space. So this is a finite dimensional vector space. And using Hacker operators, we can decompose the space into one-dimensional subspaces. So I call it decomposition. The other thing I want to mention is due to the existence of Hacker eigenform, and the coefficients pretty much is behaving like the phenomenon indicating above. So for each Hacker eigenform, the coefficients are solutions. The eigenvalues of the form, there is a t-squared, there is an algebraic integral number APT, and then there is a p raised to k minus 1 with subgroup unity. And the solutions, they are algebraically integral. So you have a basis, which are Hacker eigenforms, from which we know that if you have an element F inside weight K cast forms for a congruent subgroup, then it can be written as a combination of the Hacker eigenforms. Hence, the denominator for this F will be controlled by which coefficients you use, which is called the bounded denominator behavior down here. And to prove the second observation by Ramanujan, they also motivates the developments of the Galois perspective for modular forms, for Hacker eigenforms. So the second inequality was proved by the Ling. He constructed a Galois representation. Okay, it's actually a compatible family of Galois representations of the absolute Galois group. It's two-dimensional, and such that if you look at unramified, so for Ramanujan's case, the only ramified prime will be L over here. So for each P, which is different from the chosen L, if you look at the Frobenius element under the Galois representation, which is two-dimensional, you can compute the trace and you can compute the determinant. So the Ling showed that if you compute the trace element, it will be the Ramanujan tau function's value of P. If you compute determinant, it will be P to the 11. And using purity results of this Galois representation, we saw that Ramanujan's observation on the inequality is actually true. So for the second one, it's true. So how about the story of non-congruence modular forms? Modular forms for non-congruent subgroups. As I mentioned before, if you look at finite index subgroups for any fixed index, majority of them will be non-congruence modular forms. So majority of them will be non-congruence groups. So if you look at modular forms, you can see that if I have an modular form, quite likely it will be non-congruence modular form. The first thing is one kind of not very good news is a conjecture by Olive Atkin, which is later proved by Sayre when the group gamma, it's normal inside its congruence closure, and more general by Rocher that there is no effective Hacker theory in the sense that if you want to define Hacker operator for gamma, which is non-congruence, what you are going to do is you first compose from gamma to the smallest congruence group contained. This guy is called the congruence closure. You get to a congruence subgroup above it, the smallest one. And you first apply the trace map, and then you apply the Hacker operator on here. So if you have a generating non-congruence modular form, and the very first step when you use the trace map, you will get 0. So you will lose information if you use the the Hecker operator defined by using double cosets. And with that said, the expectation for, if I consider weight K cast forms for gamma, in general, there is the decomposition for the classical case. I can decompose into Hecker eigenforms. For non-congruent subgroups, there is no decomposition in general. And so we are going to move to the next 2 questions. How about the bounded denominator property and Galois perspectives? So in the pioneering work of Atkin and Symptom in 1970, the paper published in 1971, they actually approached the non-congruence modular forms first from the perspective of non-congruence modular functions. So they actually gave a kind of the starting point for their approach will be, if I have a modular function, if I have a function on the upper half plane, it will be a modular function for some finite index subgroups. If and only if itself is an algebraic function of the modular J function with control ramification. So such that its branch points should be only branch points of order 2 for those whose J value is 1728. And the branch point above J to be 0, its control has to be 3. And the branch points at infinity could be a little bit more loose. So it could be anything above J is infinity. So using this concept, they are able to recognize if I have algebraic function, which ones are modular functions, which ones are not. So the study of modular functions, if you put together modular functions for any given group over here, they are forming a field structure. To describe this field, basically, is to describe the coverings of your fundamental domain with the standard fundamental domain for SR2C. So it's also more or less equivalent to the study or computing the value maps, which has been actually a lot of following work and developments of value map attained by many researchers. So I listed a few over here, including there's a paper by Professor Birch, and Boykes, Montanus, and many papers of John White and collaborators, Clark and Sidling, and also Professor Molian also have done one very amazing, he has done very amazing work for computing highly non-trivial value maps. So I'm not going to mention every single work, but I'm going to switch gear to another thing in the paper by Atkin and Symptom. So they studied the first few non-congruent subgroups carefully. Of the first one they started is a kind of smallest index, which is 9. And they discover, which is later called the Atkin and Symptom congruences. So let me illustrate by using, this is the theorem stated in their paper in the context of elliptic curves. So they discovered that when I have a fixed prime number p, as long as it's not 2 and 3, if you look at an elliptic curve, which is y squared equals to xq minus bx minus c, where b and c are 2 elements, they are integral theoretically. So b and c will be inside Zp over here. Then they said that pick any uniformizer. So you write down x in terms of the uniformizer c. So as a modular function, x will, one way to do it is you can choose a double pole at infinity. That's why you start with c to the minus 2. And you can actually kind of expand it out as long as those coefficients are also p-adically integral. And similarly, you also expand it y in terms of the choice of uniformizer. And this time, to even out everything, y will start with c to the minus 3. And there is also assumption to be the later coefficients to be all p-adically integral. And once you have expanded x and y, you can write down f, which is the more or less one way to write down the invariant differential dx over y. And so if you write out using this recipe, it will becoming a formal power series, start from the local uniformizer c and raise to higher powers. And the coefficients are denoted by an. So this process is pretty flexible that you can use any uniformizer of your choice. The only condition will be I will write the coefficients after expanding out to be p-adically integral for both x and y, and consequently will be the coefficients for the differential. And if you do that, they discover the coefficients down here for the invariant differential. It's going to be satisfying a very similar three-term recursion like what Ramanujan discovered. So if you look at the coefficients attaining from the invariant differential, do it kind of consecutive one according to T, which is the fixed thing at the beginning. So if for any integer n over here and any power r, what you do is you go to the previous one, which is 1p power less, and go to the another one, which is 1p power less even, with the convention that if this becoming negative, the whole thing value will be 0. They discover another three-term recursion. There is a coefficient for the linear coefficient. They gave a formula, which is computed using the Legendre symbol. And this coefficient, which is before in the Link's result is the determinant, again is the power p. Now it's p to the 1 power, and you can see that the corresponding background will be way 2 and minus 1. And it was before the modularity result, the modularity theorem. But what they discovered basically is if you look at the invariant differential, they will satisfy three-term congruence relation. It's congruence in the sense that it's not exactly 0, but it will be 0 modulo higher and higher powers of p. And another amazing thing is just like Ramanujan's results for any choice of additional multiple you can put down over here that will not affect the congruence property down here. So this is actually, they already discovered a connection between this differential, and there are recursion, and there is a relation with later, if you put into the setting, your elliptic curve is defined over Q, you can interpret this A as the AP's coefficient of a way-2 modular form, of course. You'll see the connection to modularity that I will also mention later. Okay. Any question before I move on? All right. So then let me mention about Sou's result. All right. And Tony So actually proved that I have mentioned that now for any gamma in this context over here, you can think about gamma is going to be a non-congruence modular form. For K, which is you can think about that for this context, it's going to be for his proof, he mentioned about even integer bigger equal than 2, but you can relax the condition to allow K to be odd. It's a finite dimensional kind of vector space. The first thing he proved is, I'm going to mention the most general result. So under suitable assumption that you can pick a basis, the coefficients are almost integral. That means you only sacrifice a few primes. It's more or less this integer over here playing the role of kind of level for the congruence case. They are almost periodically integral almost everywhere except those primes dividing this, this integer playing the role of level, and where D is the dimension. So this is the first thing he actually achieved. Another thing among many important results I would like to mention will be the following. He also constructed, like the Ling's case, there is a Galois representation associated with the corresponding weight K non-congruence modular form of the action, the representation of the abstract Galois group. So when I wrote here, I already put in assumption on the modular curve being defined over Q and infinity. It's a Q rational point, etc. And the dimension of this representation will be 2 times dimension of the weight K plus form. And like the Ling's case, you can also compute the characteristic polynomial for Bennett's element if it's unramified. So it's going to be a polynomial degree 2D, and you can read off the coefficients. The coefficients, so his construction for the L forming a compatible family. So under the assumption if the modular curve is defined over Q and infinity is also defined over Q, that the coefficients are also integers. And the solutions will have the same kind of absolute value. And more amazingly, he showed that if you have any modular form in this space, so you have any modular form in this space, which is almost periodically integral for every prime P not dividing L and M, if you read off the coefficients, just like what Atkin and Symptom have done, they will satisfy a 2D plus 1 term recursion, and its modulo, there is a weight -2, and just like the ASD case, it will depend on the R over here. It will get in higher and higher position. And another thing, Winnie Li and I noticed later, it will be, actually this bound is stronger than what I mentioned later. It's called a Subgroups bound. So he proved a collective. So he proved a collective version of ASD congruences. And what's comparing to the classical result, what's not there will be due to the missing Hecke operator. They are not 3-term ASD congruences in general. Okay. Now I'm going to mention about my joint work with my several collaborators. The first thing, the first result I mentioned in my joint work is with Professor Winnie Li and Zifeng Yang. The paper published in 2005. The motivation back at those days is we consider a case resurface, which is a 2-dimensional kind of Calabi-Yau. It's a generalization of elliptic curve. So for the case resurface, we consider it's a picker number 20. So it's one of the very kind of case-free surfaces with a lot of symmetries. In particular, this case-free surface can be also considered as an elliptic surface. So it has an elliptic vibration. It's a family. Another way to think about it is a family of elliptic curves. So then we can consider the monogeomic representation is the variation of the elliptic family. The monogeomic group turns out to be an index 2 subgroup of gamma upper 1,5, which is the matrix. It's a 0 here, 1, 1, and star mod 5. Okay. And this group, gamma 1,5, is a congruence group, has 4 cusps. And in particular, it has 2 weight-free Eisenstein series. We call it E1 and E2. They both have, when I expand it out in terms of Q, it has integer coefficient and it vanished. Both of them vanish at almost all the cast form of them except at elliptic modular surfaces, we know that wave 3 cast forms for the monogeomic group. So the monogeomic group is its index 2 of gamma 1,5 can be computed in the following manner. I have E1 and E2 both wave 3. The product is wave 6. And the product is also cast form because the property I mentioned up here. So if I take the square root by using the idea of Atkin's Symptom diagram, I get the wave 3 form. All right, the H2 I wrote down have a Q expansion because E1, E2 have Q expansions. It's of this form over here is Q to the 1/10, and then there is a rational number and Q to the 3/10, and then another rational number Q to the 5/10, etc. And yes.
Sorry, yeah, I just wanted to know if is there an underlying hypergeometric equation of degree 3 somewhere?
There is this is a 4 point. All right, this is a 4 singularity. So the hypergeometric would be 3 singularity. Yeah. So
that's right. Yeah. So some generalized. Okay. Yeah.
So
that's right. That's right.
It's over here because of no problem. The process I'm taking square root actually introduced a lot of 2 into the denominators. And this guy, the H2, if I write in terms of Q raised to 1 over mu will be the cast width and infinity. It will have unbounded denominators. So that means I can multiply any integer which is not 0 to annihilate all the denominators. So it's unbounded denominator for this H. So we know immediately we are getting into a non-congruence modular form of this. On the other hand, there's also theory that I showed that you see.
Ling, sorry, there is some disturbance right now. We cannot hear you or see your slide. So let's sorry, there is some disturbance right now. We cannot hear you or see your slide.
Really?
Yeah.
Can
Can someone else confirm this, or only me who is experiencing this?
I also cannot see.
Okay.
No, we see.
Okay. Hi, Ling. Your slides came back.
Maybe I need to charge my laptop. Sorry. Sorry, maybe I need to charge my laptop. Can you see?
It is better. Yes, your slides came back. Yeah, maybe your laptop.
Yeah, my battery is almost out. Yeah,
okay.
Sorry. Yeah, my battery is almost out. Okay, so let me continue. And by Schilder enunciate that we know the L function, or that means when I compute points, the zeta function should be relating to a modular form. And in particular, the modular form will be this one in terms of eta function, eta for z to the 6. All right. So this result is actually attained by another paper by Steenstra and Boykers. We know this is going to be the wave 3 modular form. And then the motivation at that time we are facing is I have this H2, which is non-congruence wave 2 cast form, and now we have this congruence modular form, which is wave 3. And what's the relation between them? It turns out the relation between them is precisely the ASD congruences. So if I use the H2's coefficient and put them together, and I let the kind of consecutive p powers, they are relating by a 3-term recursion, and in between the first coefficient will be the p's coefficient coming from the congruence one, And then their determinant will be the determinant of the corresponding Galois representation is P squared. It's a CN form by chi minus 1. So there is a plus minus 1. And the power is modulo 2 to the R. Okay. So that's what we discover. And then we also actually find the patterns when I get to another group, which is gamma 3. And our result published in 2005 caught the attention of Olive Atkin. So he called this group to be the group I mentioned in the previous slides, gamma 2, and this case over here, gamma 3. We call them character groups. So character groups in the sense that, so in the current situation, there is no Hacker operator, but he immediately kind of reminded, because in his work, he studied economic involutions. So he called these character groups in the sense that these groups have a highly non-trivial normalizer in SR2C, which you can use to decompose the corresponding space of K-cast forms. So that the space can be, depending on K, you can get to one-dimensional pieces as well. And he computed many more cases, including generalization of our result. There he used different combinations of our Eisenstein series E1 and E2 and making suitable combinations and then constructing ramified towers. And he knew for sure there will be modular forms, and then testing the ASD congruences for the first few cases and identify very interesting cases. And this case is the congruence case, but he verified. And he did these cases and the last one corresponding to Hilbert modular forms. Right, so I want to show you a picture of Olive Atkin. That's a picture that's took in March 2008.
From Chicago, or?
Sorry?
The picture is from Chicago, I guess, or?
This one is the picture took in 2008, which is a conference at UIC. It's University of Illinois at Chicago.
Yeah.
Yes. This is Olive Atkin and Winnie Li in the middle. And based on his numeric computation, for the case when we get to gamma 4, the results as follows. So if you look at the new space, there is a O space over here. There that I skipped, there are two elements, there are two generators for the new space. And based on those results, we have a 4-dimensional Galois representation. What we saw first is the Galois representation is modular in the sense that there is a companion congruence modular form F of the same weight 3 and level 256. And the modularity is stated in the following way. You start with this congruence modular form. You look at the links representation for any L of your choice. You first
Can
No, speaker is not
if someone has, I think somehow the computer got warm, so probably yeah. So if someone has a phone or something, can send her a message.
I have a phone number, but we will send him email.
Okay. Yeah.
recording can be paused. No, pause recording is possible.
That's right. Yeah, sure. If there is anyone from the technical committee here, they can. Who is taking care right now? Yeah.
Yeah, it is paused now. That's good.
Is it?
It is paused.
Yeah. Okay. Okay. Ling is back. Yeah.
Yeah, now you can start.
I have no idea why I use so much of my battery. sorry.
Please start
Really
recording.
apologize. Yeah, it's I think, okay. Can you see my slides?
Screen
No.
is visible, but not
No.
slides.
Okay, let me try again. I think when I got kind of excited, my computer also got so excited. Oh, use all my battery right away. Okay, connect to my, okay, yeah. Need to connect it to my, all right. How can I trust myself? It asked me to trust myself. Hey, come on. All right, is it back?
Yeah. That's back. Yeah.
Sorry. And so let me just try to finish what I'm trying to say over here. So we have a degree 2 Galois representation from the modular object, which is congruence. We first do a restriction to an index 2 subgroup. So this is the absolute Galois group for this Q joining square root -1. And then we tensor with all the 4 character of this GK. So this is all the 4, the corresponding, all the 4 extension will be this Galois extension of Q joining square root -1. And then we further do an induction. After we have done this kind of patching all together, we saw that it's isomorphic to the degree 4 Galois representation corresponding to the space of non-congruence modular forms. And because of this modularity, which is proved by a method, it's like comparing coefficients due to Serre and made effective in this case by Liflet. And from then, we can prove there are 3-term ASD congruences. And the basis, if I look at P over here, the choice of my basis will be depending on whether P is going to be 1, 3, 5, or 7 modulo 8. There are 4 different possibilities I have to put together for the ASD congruences. But we saw that it's doable. Okay. And due to the example discovered by Atkin, and there are a lot of symmetries in his discoveries, we further extend the result to degree 4 Searle representations admitting quaternion multiplication. And we came up, the last joint paper with him is actually published after he passed away. We saw that if you have 4-dimensional Galois representation coming from a non-congruence modular form admitting quaternion multiplication, then this representation is going to be modular if you are knowing it's the quaternion multiplication is over a biquadratic extension of Q. All right, so the idea was done by using Clifford theory and using Tick's vanishing theorem on Galois cohomology, and also at that time the newly established Serre conjecture on the GL2 Galois representations by Curie, Winter-Rocher, and Kissing. So the result also used a relation among coefficients for non-congruence modular forms and congruence modular forms via the three-term ASD congruences. And in 2019, so this joint paper, besides Atkin, Winnie Li, there is also another author, which is Tong Liu at Purdue. With Winnie Li and Tong Liu, we further extend the modularity to any more general. Now, this doesn't have to be four-dimensional. It's any 2D dimensional semi-simple sub-representations coming from source representation. And what we call these cases to be too isotypic in the sense that if I'm doing a restriction of my Galois group to a finite index subgroup of the abstract Galois group, it's becoming a direct sum of two-dimensional isomorphic representations. Direct sum of two-dimensional sub-representations that are isomorphic. Okay. And the other thing, we assume it's F also contains a solvable extension K, such that very similar to the result I mentioned, there is also induction going on. For those cases, we can show that rho L are all automorphic. And why we want to show cases are automorphic and any applications of that, I want to mention. This is a one result Winnie Li and I proved in 2012. It's the relating to the unbounded denominator conjecture. The statement is, it's actually commonly believed holomorphic class form with algebraic coefficients. If you want to recognize whether it's congruence or non-congruence, all you can do is to look at the coefficients. If the coefficients have bounded denominators, then it will be congruence. Otherwise, it will be non-congruence. So it's congruence modular form if and only if the coefficients are bounded denominators. So what we actually proved in 2012 is if I have a space which is one-dimensional and the modular curve is defined over Q, then this generator for the space is going to be a congruence modular form if and only if the coefficients are bounded denominators. And the idea is actually using the modularity because if I start with any form F, I can use the Dirichlet theories, the Dirichlet L function. And the space is one-dimensional. The modularity results tells me I will going to get a modular object. So the modular object comparing to my current Dirichlet L function, under the assumption if this F have bounded denominator using ASD congruences, plus this is a cell bus found for the coefficients of this any finite index subgroups class form of ray K. The coefficients growth is bounded by the m over here raised to the way over 2 minus 1/5. So if it's going to be a congruence, it's -1/2 plus epsilon, but that's good enough. Using ASD, we can show that up to a twist, finite twist, these two L functions will be the same. Forces, bounded denominator implies F is congruence. And of course, a proof of the unbounded denominator conjecture has been announced this year by Caligari, Dimitrov, and Tam. And the last thing I would like to mention is the UBD conjecture is not only interesting in the context of modular forms, but also interesting in the context of vector value modular forms. And because of a kind of a discovery, they actually find in the VOA, or rational conformal field theory, that I'm going to mention in the last slides, all right? The early results in those directions obtained in many papers of Jeffrey Mason and his collaborators. So the context in the rational conformal field theory is that if you have a VOA, and then you will come up with a representation of the SR2Z. So it's a finite dimensional vector, it's a finite dimensional representation. The dimension is relating to how many simple objects you have for the V modules. And they have actually a result due to Zhu in 96. Using the simple objects, you can come up with a vector value modular form. And the transformation is of this particular shape over here. And then they also have the weight corresponding to a degree in VOA context. And when you look at in the VOA context, the vacuum object, if you look at the corresponding trace form over here, the coefficients are actually computed by dimension of the irreducible representations, hence are all integral for the vacuum object. And they would like to know when the kernel is going to be a congruence subgroup of SL to Z. So it starts from SL to Z. In the VOA kind of application, they would like to know when the kernel is going to be a congruence modular form. So it's approved by a totally different method, which is my colleague and Richard Ng with collaborators Tong and Liu. They saw that in those contexts, the representation of SL to Z, the kernel is going to be congruence. And hence the character functions are all congruence modular forms. Okay, I think that's all I want to say. Sorry about all the inconvenience.
Thanks a lot for a very nice talk. Any question?
Yeah, thank you. Nice talk. Yes.
Yeah, I just a small question, like for the gamma 1,5, that was congruence subgroup, but genus 0, right? If
it's a genus 0, yes, indeed.
Yeah, and so that's why I was wondering that why not there was some hypergeometric was involved somehow, because there was a K3 was there, genus 0 was there, and
if you want to get to the hypergeometric object,
I mean, it is true that it is not directly, like if I look at the forecast, so those like stop me, but since it is a genus 0, so the hopped module probably somehow coming from the solution of some degree 2 classical hypergeometric, right? Hello? Sorry.
Yeah. So this is a gamma 1,5. So I forgot, maybe if you go to, I forgot the case that there is a bigger group, which is gamma 0,5.
That's right. Okay. Yeah.
So gamma 0,5, I forgot. So I don't want to say for sure. That might be the 3 singularity kind of object in your mind. Yeah.
Yeah.
So I only remember for this talk, I go over there are 4 singularities and no elliptic points. So I only want to say that for this case, we are facing a K3 surface with in the object, the monogeomic group for gamma. It starts from gamma 1,5. Right? The one I want to mention, gamma 1,5, it has 4 singularity. But I know that in your mind that you might be looking at gamma 0,5, and I forgot how many. I mean, maybe this
gamma
is
0,5 also has 4 cusps. So like, yeah.
Yeah. So.
Sorry, gamma upper 0,5. Yeah, that I remember. Yeah.
I mean, it's the conjugate to gamma 0,5, whichever
yeah,
one.
Okay. Yeah.
It just happened that we fixed that notation. For this situation, we do not see the role of hypergeometric function. And of course, it's actually when I get to this result we mentioned about with Winnie Li and Tong Liu, and then we see the QM coming in. After we saw the QM come in, one of my motivation is to construct a lot of kind of 4-dimensional Galois representation with quaternion application. And that was actually the motivation leading me to other joint projects on, finding 2-dimensional abelian variety with quaternion application, and then finding the solutions leading to hypergeometric functions. It's one of the motivations why I actually kind of went to a different direction starting from here. Yeah. But definitely, this is hypergeometric functions is another perspective complementary to what I said. It's closely related, especially if we get to supercongruence with Ravi and Ramakrishna. We prove some results on truncated hypergeometric functions, super singular, super congruences.
Yeah, this is with the Hawley and Vadim, right? Together.
Yeah, not Hawley. So in my more recent paper just appeared, which is with Fountain 2, my colleague Fountain 2, which is Noriko Yuri and Vadim Sudu. We did Clabial 3-4.
Right.
And a rigid Clabial 3-4 super complexes.
Yeah. Okay.
And yeah, I actually gave 4 talks on this topic, which is the link. There is a link on my website on the video recordings. Yeah.
There was one quick question, like before. Yeah. So the UBD, the conjecture, which was announced recently by Caligari and all, this is like up to what extent is completely resolved, right? Or there are some conditions involved with this, the proof?
I think the setup, the approach over there is, I went to, one of the talks by one of the authors. And so they have some very reasonable assumptions because the UBD conjecture itself also have actually kind of a lot of different ways you could state it. You could focus on one cusp. They focus on one cusp.
Yes.
Or you focus on expansions and on all cusps, etc. Yeah, the setup that the talk I went to, I think it's a general approach using a more analytic kind of perspective. There is
they didn't use vector valued modular form, right? Like that's what I think
it's actually that's a vector value modular form for there.
I see. So then they look in one component at one cusp, the expansion, if there is a P growing fast enough.
So their idea is if you have something violating the bounded denominator conjecture, they have a machinery to come up with more. And then there is the contradiction comes in that if there is more, there is a bound for how many you could have. And then you would see a contradiction. Yes.
Thanks.
And
Thanks a lot.
It's a kind of very kind of nice new idea how to approach it.
Thanks a lot. Are there any questions from the audience?
No, I think.
Okay. Yeah. Thanks a lot, Ling. It was a very nice talk.
Ling.
Yeah.